We now have some notion about how to thermodynamically characterize a state of equilibrium in a chemical reaction. What I'll say about this is that most chemical reactions actually achieve that equilibrium state relatively quickly. So we can expect that most reactions that we examine are at an equilibrium state. In fact, it's fairly rare to see one in a non-equilibrium state. The question we want to ask in this lesson is, if I start with a reaction that's at equilibrium and I somehow change its conditions, how will that affect the equilibrium? So in other words, some of the changes that we'll be considering in this include things like the temperature. For example, I change the temperature. What effect does that have on the position of the equilibrium? I could change the pressure also. These are things that we hold constant when we run these reactions, but if we now were to run this reaction, let it reach equilibrium and change them, how might that affect the equilibrium? Another that I might impose is a change in the composition. In other words, I could add more reactants or add more products. How does that affect the equilibrium position? Now you may recognize some of this as basically being the elements that go into something called Le Châtelier's principle. And this is something that we usually cover in general chemistry. And it is in fact the central theme of this entire lesson. What we want to do is understand what is the thermodynamic basis for Le Châtelier's principle and how can we understand it a little bit better. All right, we're going to use as our template for understanding this same hypothetical reaction that we've been using in other videos and earlier in this lesson. And what I want to do is examine for a hypothetical reaction like this, how we can get a handle on changes to the Gibbs energy and how that indicates what happens in the reaction. So I'll remind you that at constant temperature and pressure, we can write down, actually I should write this as a differential of G. We can write the differential of G as simply a sum over all the components in the reaction of their chemical potential times a differential change in the number of moles. And we have seen that in fact we could write this also in terms of a term called the reaction potential times a differential in the extent of reaction. All right, and this is a very convenient way to go because now we have just a single parameter that's basically taking us from one end of a reaction to the other end and doing it in a controlled basis, in a controlled way that maintains the relative proportions of the composition of the mixture. Now, what I want to do is use this to examine this quantity, and that's the quantity that we're really going to care about when we talk about changes in a reaction. Now, I'll remind you that one of the results that we've obtained in earlier parts of this module is that this could be written in terms of a reference value, and this reference value we've seen can actually be calculated from tabulated values for the Gibbs energy of formation of different components that appear in a reaction, plus RT times the log of a reaction quotient. Okay, and this reaction quotient is basically something, and if I'm going to do this for a gas phase reaction, for example, it would be simply this function of the various pressures that appear in the reaction. So if these components up here are all gases, I would end up with an expression that looks something like this, where I have each of the partial pressures raised to the power of its stoichiometric coefficient. All right, so this reaction quotient is basically going to tell us where we are in this reaction in some ways. At equilibrium, we also know that the value of this quantity, delta Rg, is equal to 0. So that tells us that this delta Rg0 can be set equal to negative RT times log of the equilibrium constant in terms of pressure. So what I want to do is, as at least an initial indicator, combine these two equations. So I've got an expression here for delta G0. I could just plug that in here, and what I would end up with is an equation that says that my delta GR, that is the piece that belongs here, is equal to negative RT log of the equilibrium constant plus RT times log of my reaction quotient. And I can combine these now just using a simple property of logarithms, that if I have log of A plus log of B, and let's actually make this more interesting, negative log A plus log of B, that the result is going to be log of B over A. So if I use that property of logs, I can write this very compactly as RT log of the reaction quotient divided by the equilibrium constant. So now I have a tool that I can use, and I'll say that this thing that I've written here, this thing here, is basically the key for determining the response. So it is the thing that we want to focus on throughout this lesson. All right, so what we'll want to do is figure out when we change different things, when we change different qualities around the reaction, how does it affect this? All right, temperature, we can certainly heat up a reaction, raise it to a different temperature, and that may affect things. We'll see, in fact, that it does. But it won't affect things if it does not affect this, because this is basically setting the balance of the reaction. All right, now one of the things I want to point out is that if Q is equal to Kp, if at any point along this way, then what I'm going to have here is log of the number 1. And log of 1 is equal to 0, so that automatically tells me that this is equal to 0, and that's what I should expect to find at equilibrium. So at any place along the way, if I end up with Q equal to K, I'm at equilibrium, and that's the end of the story. So what we want to do is consider when conditions change, what is going on? What could we look for? All right, so let me put this down as possible changes. And what I mean by possible changes is what can I look for in this equation that deserves focus? Well, I'd say the first thing is we could have a change in delta Rg. And that really is a change in the equilibrium constant. Okay? And what this will mean in terms of before and after shots is that my initial state, that is when I'm initially at equilibrium, in that state I'm going to have Q equals Kp. Okay, we're in a state of equilibrium. In my new state, what I'm going to have is that Kp is going to go to some new value. So that means my ratio of Q over Kp is in fact going to equal essentially K of my original mixture, K old, divided by K new. All right, so it's evaluating what this is doing between the old and the new that I would be caring about if this is the place where I'm focusing my attention. All right, there's another place though that I could focus my attention, and that is if I have a change that affects Q directly. And I'll just say, for the sake of argument, changing the composition is going to change Q directly. So if the change affects Q, then my initial state is no longer going to be Q is equal to Kp. Now what I've done is I've altered Q, so Q does not equal Kp. And in this particular case, my ratio of Q to Kp is effectively going to be Q new, the new Q that I've created from that change, divided by the same K, which was my old equilibrium constant. Now, the way that the system needs to adjust is as follows. When this is my mode of change, what I'm doing is I'm changing the rules of equilibrium. I am basically saying, you might have been at equilibrium before, but I've changed the rules and you're going to have to adjust. When this is the thing that we're focused on, however, we've kept the rules the same, but the system has changed and it now must readjust to re-achieve equilibrium. So let's see how those things work in the next few videos.